Good morning. My name is Stephanie Smith, and welcome to Risk Management Professionals webinar series. Our producers, Sarah and DJ, are here in the background to keep us operational and take any questions. We have a special dialogue box for that in your controls. Feel free to use that during the presentation to submit questions, or if you have any comments, if you're a regulator, want to add in a little bit of comments, we're happy to take those as well. Typically, we send those after, but we can also address them during the presentation. And as far as getting help, there are two phone numbers in front of you. If you printed out the presentation, you'll also have those. If you have any audio problems or need any help, we have people here that can try to help you with any IT issues or audio or signing in or whatnot. So go ahead and give us a call. The 877 is a toll free if you need to reach us there. The image sizes also adjust. A lot of people are pretty used to GoToWebinar by this point, but just so you know that the screen sizes and the presentation size will adjust. You can also move that video screen around a little bit with my video on it, or if you just want to see the presentation, you can go ahead and get rid of that altogether. So you have some adjustments you can make as well. And then we will just jump right into the RAGAGEP presentation. Real quick about our background. We have a lot of experience in safety consulting, mainly around the RMP and PSM regulations, but we do extensive other work, also specialize in some state regulations. Here's a quick list for you. You can take a look at your leisure. This is the last of the series for RAGAGEP. I'm sorry to say you will not see me as much talking about RAGAGEP anymore. I'm sure there'll be plenty of other topics in the future, but I wanted to tie this up, excuse me, with the chapters 15, 16, and 17, and just a quick summary of the appendices since most of them are informative. 15, 16, and 17 are actually probably some of the easier IIAR 2 chapters to implement as RAGAGEP. So I'll spend a little bit of time on that, and there's some extensive information, but we'll go through it, and I'll try to keep it as painless as possible. This also is a reminder that IIAR is for new system design, not existing systems. So this whole series has been based on IIAR 2 because there is no IIAR RAGAGEP standard yet, and we'll get into that later. IIAR 9 is in progress right now, and I have some dates that they're projecting out for the release of that. So this presentation, as with the rest of the series, is formatted to take IIAR 2 and help you implement and address issues that may be assigned to RAGAGEP under new design standards. Again, IIAR 9 is in progress, also IIAR 6 about the safe operations of the system, so more into your maintenance and operating procedures, will also be developed around the same time frame next year. And again, we'll talk about that a little bit later in the presentation. It also is really important to remember it's never too late to start implementing RAGAGEP. Even if you're unsure, every little bit helps. Any assessment on what can be safer for your system helps. We'll go through some quick definitions. A lot of them we've talked about before, but I always like to refresh and review for the ones that are most important for the presentation I'm giving. Authority having jurisdiction is basically your regulator or anyone else locally or federally or anything in between, where they have the responsibility of enforcing these standards. So there's a number of AHJs you could be looking at. Generally speaking, we're looking at the regulator for the facility, whether it be local or all the way up to federal. Authorized personnel applies to those that are trained and authorized to do a particular task or access a particular area. So it's really important. This is a big one. Whenever this is used, they're basically talking about authorized operator, authorized mechanic, someone who has the keys to a room that not everyone else has. So it's really important that that's this definition and this difference between that and all the other employees on site. Generally speaking, equipment is everything associated with the refrigeration system. I actually had this come up in the last few months where someone said, well, we never thought piping was part of the refrigeration system. And I had never heard that before. I didn't know that that was a challenge for some people, but it does include piping, your large equipment, valving, controls, anything associated with the system with controlling operations and maintenance is part of the equipment, generally speaking. It's really important for that distinction. Maximum allowable working pressure is essentially the max pressure a vessel can operate at. This is for a normal operating position and designated temperature. So it's usually pretty specific because pressure can vary so much between temperature ranges and things like that. Pressure relief valve, we're going to talk about these a lot today. Essentially, it's a device that relieves pressure. I think most people understand that. I pulled the definitions for the 3 pressure relief valves discussed in IIAR. The hydrostatic relief valve is essentially designed to relieve pressure where liquid can be trapped. Pressure relief device is, more generally speaking, something that would automatically relieve excess pressure. So that could be vapor or liquid. It's just a more general term. And the dual pressure relief device is basically your three-way valve setup that we typically see with the 2 pressure relief valves. And so you can isolate one and replace them and whatnot and have a backup. Readily accessible is another big definition we've talked about this whole series. Readily accessible refers to anything that you may have to access as far as equipment, piping, valving for maintenance or operations. Essentially, if you have to get on a ladder or you have to climb down a catwalk and twist over and lay down backwards to access a valve, it's not readily accessible. So this is stuff that's at normal person level. It can be up on a catwalk if the catwalk is easy to get to and it's easily accessible from the catwalk. We're just talking about no ladders and no weird contortions of the body to access things. Shall not and should not are always terms I like to bring up. Shall is the mandatory provisions. Should are the recommended provisions. And basically it goes that even your shoulds should be followed if you can reasonably do that. And shalls are a mandatory thing. And 3-way valve, going back to our dual valve PRVs, basically a service valve that has manually operated valve with 2 connections. So we'll talk about Chapter 15 in overprotection devices. 15.1 is a general clause. That is, sorry, I'm adjusting my text a little bit here so I can see better. It's basically saying that pressure relief devices are going to meet the standards of this chapter. Almost every chapter has this general clause. I don't always write it in here, and this is one of those cases. The overpressure protection devices do specify that excess pressure will be relieved due to fire or other abnormal conditions. Again, pretty self-explanatory. Most of us know that, but for the sake of stating the requirement, I like to do so. 15.2 for pressure relief devices just lays out some general requirements. One being that the system has to have at least 1 pressure relief device. Basically, you need to be able to relieve the pressure from anywhere in the system. And they must meet the ASME boiler and pressure vessel code. That comes up a lot. IIAR2 references that a lot. That's basically their mechanical standard or their material standard for most of the equipment in this standard. So you'll see that a lot, especially in this presentation for each device. The installation always should allow for the inspection, maintenance, and repair access, and this also goes back to readily accessible, that these should be readily accessible for access for any of these tasks. And if you're using it for vapor service, the pressure relief device should always be connected above the highest liquid ammonia level. That being said, there is an exception for that on, say, oil pots, where you may not be able to connect it higher than the anticipated liquid level, but you would just put it on the highest point of the oil drain pot instead. So there is one exception to that. If you're familiar with refrigeration, then you look at the designs, you wouldn't want to put your oil drain pot above, say, your compressor or something like that, where you wouldn't be able to drain your oil. So that they give you that exception. The overpressure protection should also be installed as close as possible on the equipment being protected, and it applies to all similar applications. So if you have any other applications other than pressure vessels where you may need pressure relief, the same standards would apply to those applications as well. 15.2.5 basically states that you need to prevent moisture from getting in the valves. or the relief vent line. I think we can all understand what metal and water do together. You would have a lot of corrosion and it would just be a nasty mess. So having those vent caps, having some kind of protection for that valve body against moisture, having everything properly sealed, possibly even coated or painted, that is all going to help protect that emergency protection that you're trying to have with installing these valves. And also for setting pressure relief devices or installing them, the pressure and of the valve or the device and the rupture member, if you use those in series, shall not exceed the design pressure of the equipment. Pretty self-explanatory, but you'd be surprised what we see as engineers. Basically, if you have a pressure vessel rated at 300 psi, you don't want a relief valve rated at 350. You'd like to go down below 300 at a reasonable level in order to protect that vessel. Also, some kind of means to detect pressure buildup. Usually I see a gauge. There may be other methods. Perhaps you have some controls going back to your control system. Whatever works for a facility and whatever stage your facility that, there just needs to be some method of detecting the pressure. As far as marking relief devices, they all must be set and sealed according to that boiler and pressure vessel code. And those requirements, again, are pretty standard for most equipment. The resetting, any kind of resetting done must be done by the manufacturer or a company holding a valid test certificate. So if you're getting these tested, they either have to go back to the manufacturer, has to be someone certified. It can't just be anyone testing this equipment. Instead of, I know a lot of programs will reinstall new valves and just get rid of the old ones. So if you're testing it, there are some requirements for that. Also, the capacity has to be stamped on the device or available upon request. This kind of ties into your PSI. You should always have this information available, but especially so with your protection devices. The capacity is stated to be require either SCFM or cubic meters per second, or in pounds of air per minute, or kilograms air per minute at 60 degrees Fahrenheit. So they should all be rated at 60 degrees and then have some kind of flow rate associated with that. And there are specific metrics that are used for that. So generally speaking about protection, all the equipment, again, should be built to ASME boiler codes and provided with certified pressure protection. So again, going back to the manufacturer, the testing certificate, you have qualified people installing this and testing it, making sure everything's working as needed. For the liquid vessels in your system, they have to have certified hydrostatic relief valves. This is pretty standard practice now, but if you don't have them, this is an easy one to alleviate from a RAGAGEP standard. Make sure you have these hydrostatic relief valves on your liquid vessels or anywhere where liquid can be trapped. It's an easy install, and it's something that again can alleviate that RAGAGEP issue if you're looking at possibly being deficient on that. Again, these hydrostatic relief valves need to comply with the ASME code that we're stating, as well as section 15.6 of IIAR 2, which we'll be getting to in a few minutes. In addition, the sizing is in accordance with the section we'll be talking about, I believe, on the next slide, if not the one after. That's section 15.3.7. We'll talk about sizing and capacity. And pressure vessels less than 10 cubic feet of internal volume must be protected by at least one pressure relief device. No, I'm getting to greater than after. Pressure vessels, sorry, we had a question, should that be greater than? Pressure vessels greater than 10 cubic feet of internal volume shall be protected by at least one of the following. And this is where it kind of gets confusing, but I'll help explain this a little bit. Either one or more dual pressure relief devices installed with a three-way valve or a single PRD. So you have the option to, and again, these are minimum standards. You should always go with the most safe standard that applies, or the safe installation. But you can have a single PRD, or they give you that extra, well, maybe you should put some dual PRDs on these. Have that backup plan just in case you have an issue. It's really based on the volume. You don't want that pressure to build up where this large volume would be an issue. And so there is a little bit of difference at that threshold, but essentially they are the same requirement. In addition, the dual PRDs must comply with the sizing that we're going to talk about on the next slide. They must set to a fully seated position, and the sum of the capacities must equal or exceed the requirements in 15.3.7, again on the next page, so we'll talk about that. The three-way valves must allow for testing or repair, and when you talk about the single PRDs, the vessel can be isolated and pumped out in order to maintain that device or replace the device. And they should be on the low side of the system if you're only using one. So we're talking about the low pressure side of the system. Any other pressure vessels that are separately protected, they can be in accordance with the same section 15.3.7. As far as the discharge side of the PRDs, basically the receiving portion should be able to discharge the increased capacity of the PRDs. So you cannot basically pinch the flow. Whatever you may be discharging as far as capacity should always be protected on the other side and be able to be received on the other side. Hydrostatic overpressure is the exception to that rule. And there are two different kinds of pressure relief valves that are allowed to be used in this circumstance. Basically, you don't want your pressure relief valves to be affected by back pressure. And in order to do that, there's a lot of detail as far as how they're affected by back pressure and how to protect the vessels. So go and look at this section. It was too much to put into a discussion here as far as the specifics of 15.3.6 in relation to how to use these valves and back pressure protection. So I encourage everyone to go and look at this section and read it. It's pretty detailed as far as how to protect that device. The hydrostatic overpressure protection, basically they can be discharged to other portions of the system as long as those portions of the system are protected by PRDs. And again, in accordance with all the sections that apply, they would be like normal pressure relief devices, just a different part of the system, but you can connect hydrostatic relief back up into a different part of the system. For instance, if you want to put it back into a large vessel, it can handle higher pressure. For 15.3.7, this is the capacity and the determination of flow rates and everything we've been talking about, so I'll go through this a little bit. Basically, there must be sufficient mass flow carrying capacity within the vessels and within the relief protection system, the whole system, not just the valving, but the piping and everything that goes along with this part of the system, basically to prevent catastrophic failure. You don't want your emergency protection device to fail. That's your last resort. In a perfect world, we would have nothing go wrong and you would never use the pressure relief devices, but that doesn't always happen. And so this is your last resort and it cannot fail is basically what this is saying. So to ensure that you have plenty of capacity there. And they've listed out a number of considerations, including fire, any kind of isolation that will result in thermal expansion, some kind of internal heat load, and then there's this general other. Basically considering any other overpressure conditions that may cause some issues in your system and utilize the pressure relief system, you need to account for all that capacity. The minimum relief capacity depends on the equipment, the effects of the inlet pressure losses, and scenarios under which overpressure is being created. Again, going back to the second bullet of all those considerations that you have to take into account. Also, they must include heat loads and from cleaning operations and process loads. So any kind of extra heat load that may expand your gas in the system is a possibility for extra capacity or overpressure. So those need to be considered. Manufacturer data can be used to determine the requirements. If you have your own data or better data from your operations, absolutely, that's fine too, but they do allow you to just use the manufacturer's recommendations. Applicable heat loads that can cause overpressure must be considered. We kind of talked about that already. And the largest capacity requirements for scenario must be the one you're using. So if you have different scenarios you're looking at, perhaps different valves that you think might relieve or whatnot at the same time, the largest capacity has to be the one you're using to evaluate the needs for the system. And there are formulas in IIAR2 specifically for pressure relief capacity. Take a look at those. That's a good guidance as far as how to do it, what to consider. There's all the factors are in there as far as conversion and things like that. So those are good resources. The capacity factor should be increased to 1.25 where there's combustible material within 20 feet. That's just a general standard. And the discharge capacity, again, should follow the ASME code and markings in accordance with 15.2.7, which we already talked about, the capacity rating stamped and available. Again, going back to your PSI, making sure you have all that information available. There's also equations for discharge capacity under critical flow conditions. Make sure you're using those equations in 15.3.10 if needed. Stop valves are not to be installed in the inlet piping. Those need to be free of any kind of blockage or anything to relieve that pressure. Again, you don't want your emergency system to fail. Anything that's discharging to an external system is not considered part of the refrigeration system. So there is a division on where the refrigeration system ends. For instance, if you're discharging to atmosphere, that's basically where your system ends. That's an easy example. So there may be other examples of external relief, but that would be an easy one to use. Also, the stop valves on outlet piping have to take into account the pressure drop of the, and then they need to be locked open as well. So if you have stop valves, they need to be locked open, but they have to have the capacity, that diameter, to allow the capacity of that full pressure relief to go through. So no pinching the capacity flow when you're trying to discharge to another device or from another device, either or. Piping, again, going back to this capacity flow, piping should not contribute to pressure drop. Again, you don't want to squeeze that capacity or that flow down where you're not relieving properly. You want to make sure this is designed so that you have the full flow through the piping, the valve, and all the way back. In California, we're used to diffusion tanks, all the way back to your tank or your flaring system or whatever you're using for the discharge point. And then there's some specs for discharge piping sizing. There is an exception to using steel or stainless steel. Relief piping can be utilized as galvanized or ungalvanized ASTM A53 type F and malleable iron at ASTM A197 fittings. Mostly because at that point, once you're past the relief valve, you're not concerned so much about daily operation with ammonia in your system. So they've allowed for a couple other metals to be used. This is listed in section 15.4.3. So if you have any questions about that or need to look up those specs, those are sitting right there in the regulation. Again, the discharge pipe should be no less than the outlet size of the device. We've been talking about that. Just don't pinch the flow out. The minimum size and the total equivalent length shall be determined based on the sum of the discharge capacity. So you need to account for all the capacities of the PRDs if they're expected to discharge simultaneously. So if you have, three pressure relief valves that could discharge at one time, that piping capacity needs to accommodate all three of those for the length of time and the flow that might be going through there. So that's something to keep in mind. Again, it's in the equations. There's a lot of guidance in the IIAR2. Please utilize that if needed. The 15.4.5 talks about where the liquid ammonia can be isolated. Basically looking forward to 15.6, we'll talk about in a few minutes for hydrostatic relief, but basically protection against overpressure. Just general statement for the piping that there needs to be some kind of pressure relief there. And discharge piping shall be supported in accordance with section 13.4. That's going back, I believe, one presentation, might be two. And it goes back to section 13 in piping hanger supports and isolation requirements. So the structural integrity of supporting that piping, supporting the weight of the piping and contents within the pipe, preventing damage from vibration, stress, corrosion, and physical impact, and any kind of attachments or methods should support applied loads. So your civil engineering side, make sure those pipes are supported, make sure the valves are supported, and everything's just ready and against vibration and can support the load that might be going through there. Also, atmospheric relief piping should be used only in relieving vapor. You should not be using atmospheric relief for releasing liquid. That is just hydrostatic alone. I think most people who know how ammonia reacts in air, you'd have a lot of expansion of the liquid into gas, and you'd have a bigger problem than you really need. 15.5.1 talks about the vapor being discharged directly to atmosphere outdoors. This outlines exactly what's required. The maximum length of the piping shall be determined by the equations in the section. There's a section that talks about how high above breathing level or above a building height you have to discharge to prevent hurting someone else in the community or one of your employees. It's important to go look at those if that's what you're attempting to do, is to discharge to atmosphere. That being said, there are some exceptions to discharging to atmosphere, especially in California. We're required to use a diffusion tank or diffusion system within the state of California. So check your state regulations, check your local regulations. Perhaps your local regulator has a different view on things. So make sure that you're talking to your regulator if you're unsure about what's allowed where you are. There is an allowance if you do not want to discharge to atmosphere. Of course, you can discharge into something like a treatment system, a flaring system. You can opt into a diffusion system somewhere else in the country, or any other approved means by your authorization by your regulator. So talk to the authority that has jurisdiction over your area and make sure that there's some understanding on what you're allowed to do. When you're discharging the atmosphere, the discharge must be at least 15 feet above grade and 20 feet from any windows or ventilation intakes or exits. Also, the discharge must be at least 7¼ feet above a roof occupied solely during service or an inspection or higher than the adjacent roof within 20 feet. So you do have that allowance for going up onto the roof, but again, you still have to hit that 7¼ feet. If you're using a flaring system, it must be in accordance with 15.5.2, which we'll get to on the next page. And again, diffusion systems are required in California, and we'll also talk about them in 15.5.3 for those that might want to opt in or have one on their facility already. To continue the discharge piping requirements, piping must terminate greater than 7¼ feet above platform surfaces. So we're talking about catwalks and things like that. And the termination must be directed upward. Basically, you don't want to blow ammonia gas or ammonia right into someone's face, is what they're saying, and they don't want it blown down towards the ground. So being very careful of that. Again, a lot of this stuff is intuitive, but you'd be surprised what's out there sometimes. I actually have seen this situation in a PHA where they had a pressure relief relieving right into a main walkway for operations. So it was something they obviously fixed. They had a recommendation for it, but just be careful. Make sure you're looking at your system carefully and that everything is following these requirements, at least at a minimum. Also, there should be some kind of provision for draining the piping. If you get water in there, even if you are doing your best to keep water out of it, there's possible you could get water in the piping. Having some kind of drain or a way of draining that system between needs, or maybe during the dry season when you know you're not going to have rain or snow, that would be a good time to do it. 15.5.2 talk about flaring systems and that they need to be tested to demonstrate compliance with the design. And water diffusion tanks, they need to be sized at 1 gallon of water per pound of ammonia released within 1 hour. So that requires a little bit of effort as far as determining your capacity and which you should already have, but what would you be discharging, and then how much would be discharged in an hour, and then determining how much water you would need in that tank. With diffusion tanks, you also need to prevent this water from freezing. Most parts of California where it's required, we don't have that problem. Other parts of the country definitely do. So keep that in mind. You may have to do something. Maybe there's some kind of heater that you have to put on, or a chemical you can add to prevent freezing that won't affect the absorption of ammonia and the operation of this tank. You never want to, affect the operation. You want to operate as planned. But there are methods to prevent freezing. And piping should distribute the ammonia to the bottom of the tank, but more than 33 feet below the liquid level. So you want to get that down into the water. You want that water to react with ammonia, attach itself, and you basically end up with aqueous ammonia. There may be some restrictions on this just based on, well, we'll never get 33 feet of liquid level. And the discharge piping should basically go down to the bottom with just enough room to allow the ammonia to escape into the water. The tank should be large enough to contain the water and the ammonia without overflowing. So you have to account for the extra capacity of ammonia, probably have some headspace on top as well. It's also important to remember with these water tanks that water treatment and disease and bacteria and algae and all sorts of stuff also come into play with these, especially if you're in a hot climate. So those also have to be under consideration. There's a whole industry for that, and a whole nother topic I could get into. Just make sure you're addressing things as needed, and that you are testing your water, you're maintaining the system properly, and that the tank's integrity is also intact as well. The back pressure due to water being in that tank needs to be considered during the vent design. You should not have any kind of back pressure, putting pressure on those relief valves where the valves will not relieve. So making room for that and addressing that issue during design is important. Hydrostatic overpressure protection. Basically, we're talking about liquid lines and the hydrostatic expansion of trapped ammonia. This is where those hydrostatic relief valves come into play. They need to relieve automatically during normal operation and during shutdown. In addition, any kind of planned isolation should be on standby or for seasonal conditions. So if you're trying to replace them out or whatever, it needs to be scheduled and planned out. And equipment or device fault needs to also be included in its operation. There is an exception for maintenance and service operations using engineering and administrative controls for trapped ammonia. Say if you're taking that valve out to replace it or to test it or whatnot, there is that allowance there, but it should be a temporary allowance. You shouldn't be operating like that on a normal basis. One or both of the following should be used when talking about hydrostatic protection, hydrostatic overpressure protection. A static relief device or check valve should be provided to relieve another part of the closed circuit system, or an expansion compensation device. We can get into engineering of this, but basically, providing that extra protection for your system, having that backup plan. These can fail, so making sure that you have the allowance to protect that thermal expansion that could happen in trapped liquid. Frankly, it's probably the easiest to try not to design a system that can trap ammonia. If you have two valves together that don't need to be there trapping ammonia, it's probably best to just take one of them out. But with the need to isolate equipment and things like that, of course, that allowance needs to be made as well, and it is possible to have those situations within the system. And as in section 13.3.5, which we talked about in another presentation, the relief valves should not be used as shut-off valves. So they shouldn't be programmed or controlled in any way to shut off the flow. These are pressure relief devices, and they're used basically on the last need basis. So chapter 16 talks about instrumentation and controls. Again, the general statement that all instrumentation and controls shall comply with this chapter. But basically, controls should indicate the operating parameters to the system and the ability to manually or automatically control the operations of the system. These controls should also be able to provide notice of what the system parameters are and what it's doing, and if any parameters have exceeded. So having those notifications, having those alerts on the screen, that's all included with the requirements as far as the instrumentation and controls. The function, sequence, and operating design parameters shall be obtained or documented and maintained on site. Going back into your PSI, you should have this anyways if you're using controls, but to have the user manuals, the set points of equipment, how the controls are being used, your P&IDs updated with controls included on your P&IDs. All this goes into documenting what your instrumentation controls are doing. There shall be a means provided for monitoring concentration of ammonia. We're talking about alarms and sensors in the event of a power failure. And we'll talk about alarms and sensors in the next chapter as well. But those should all be connected back to the controls to provide alerts, whether it be audio, visual, or just notification. Also, any kind of safety settings that are going to be changed should be limited to authorized personnel only, going back to that special category of operators and employees that have certain access to different things. That's your protection on controlling the system, at least in part. Having these controls behind locked doors with passcodes for people to get into, with a second confirmation that you want to make a change, similar to what we see maybe on our daily computers where they ask, are you sure you want to delete this file? It's the same thing. Are you sure you want to delete or you want to change this set point? Those kinds of programming, that kind of programming will help maintain the system and alleviate any mistakes that might happen. The electrical controls, generally speaking, should comply with any electrical code that's applicable. It's usually the National Electrical Code, but there may be some local standards as well in the building codes. It's important to just check those out. And also the maximum allowable working pressure of instruments and liquid level indicators should be equal or greater to the design pressure of the system in which they're installed. So if you have a piece of equipment or a vessel or piping that you're monitoring, you must have those controls if there's anything that's coming in contact or anything that may be at a working pressure has to be equivalent to what it's connected to. So we don't want to overpressure controls inadvertently, and similar to pressure relief devices, you want pressure relief device to relieve after you've already lost your tank. You want it to be around the same and protect that. For design and selection of liquid level and indicators, basically using a performance-based design, and that you're following section 5.5 for design pressure. I won't go back that far. I think we've talked about it a few times as far as the design pressure. The requirements are in, I believe that was the second part of this series that I did in chapter 5. But going back and looking at that for design pressure of the liquid level indicators. Sight glasses and linear liquid level indicators shall not be installed where there's risk of hydraulic shock. Again, you don't want to blow out your equipment at a weak spot. You want to protect those. So making sure that those are installed at the correct points of your system. These indicators that are used to observe the ammonia levels shall be designed and installed in a manner that provides protection from physical damage. Again, protecting your system, not having weak spots as much as possible is really important. And that can be done as a RAGAGEP as well. If you're replacing your level indicator, you can replace it with something that is more robust, maybe better materials and things like that, or maybe you have some kind of electronic controls on it that work better. The indicators shall be fit with internal check type shutoff valves, again in protection against accidental breakage of the glass tube. Again, not releasing ammonia. We want to protect the system. We want to have robust materials that won't cause any issues with operations. And then we talk about bullseye sight glass types. Basically, they need to be compatible with ammonia, and they need to be sized for the application. So and traceable serial number is really important. Again, going back to your PSI and making sure that you're sizing everything appropriately. It's all important for not only design but RAGAGEP as well. 16.3, we talk about sensor controls. The sensing devices that initiate control need to have the same design pressure as the other equipment. Again, going back to 5.5, the design pressure is really important, that you don't have a weak spot in your system. It would be good to go look at that within your system and make sure that you don't have any weak spots if you haven't done that in a while. Um, these must comply with section 16.1.7 for ultimate strength. We talked about that a little bit. It's also listed in the in IIAR 2. Also documented performance history for the similar service conditions, performance-based design as well, and listed individual or as part of the assembly of the system. So having those specs on your sensor is important. Generally speaking, they will come with nameplates, and on the nameplate information, I listed this out from the regulation or from the standard. I will not go through everything, but it's your general information that's required for most nameplates as far as manufacturer, serial numbers, flow rates, electrical supply information, any kind of controls and special characteristics would be the big one. If there's anything special about your sensor controls that you need to list, should be listed. It should be on the nameplate. I always recommend taking a picture of the nameplate so you have a picture of the original just in case it fades or gets scratched or damaged, and also recording it in your PSI. This mouse today. Chapter 17 is ammonia detection and alarms. This is probably one of the easiest RAGAGEP requirements to meet, just because alarms and detection are pretty easy to install and maintain. So if you don't have this or you aren't following these requirements, I would recommend you take a fresh look at your facility and the system and see where you can improve. Here, this would be an easy one to do, in my opinion. Machinery rooms, they must comply with 6.13 and then 17.2 through 17.6, which we will talk about in a few minutes. Anything outside of machinery rooms would be a section in Chapter 7, 2 sections, Chapter 7, and the whole of this chapter. And leak detection for package systems would follow Chapter 14, a section in Chapter 14, and also this chapter. So they've kind of outlined where there may be other references for detection and alarms. We've talked about those in past presentations. I'll let you go back to those. And I'm going to be outlining them in here for at least Chapter 17. The power needs a dedicated branch circuit. You have to protect your detection alarms against power outages, and they must remain on during a power outage. This would basically be running a generator, a separate power circuit, making sure that there's no power loss to this equipment, because if you may lose the rest of your equipment and still need your alarms and detection. Testing has to be done on a schedule for based on manufacturer recommendations. It's typical for these detection alarms, but your manufacturer will know the best schedule to test on. And if there are no recommendations provided, they shall be tested at least annually. So you want to check your manufacturer recommendations. When in doubt, test annually and make sure that those alarms and detection systems are working. The sensors shall be mounted in a position where ammonia leak is expected to accumulate. So again, this would be in machinery rooms. That's a hot topic. As far as a closed room where it can accumulate, you may have equipment outside where you need to install a sensor in order to detect ammonia, say by a condenser, where you could have the potential for a lot of leaks on the roof. You may have compressors outside your facility where you need a sensor there because there's no protection of the building and containing that a little bit. So take a fresh look at your system, see if there's any gaps as far as the leak detection sensors are concerned and where they're placed, and make sure you get those installed if needed as soon as possible. The location and sampling tubes shall account for the air movement, so you don't want them near the inlet of a ventilation system, or I'm sorry, you would want them near the inlet of ventilation system, maybe not the exit of a ventilation system, or perhaps in an area where you have like a wind tunnel situation between buildings or something like that, where you wouldn't get the full effect of detection. So you want to make sure that you're in pretty stable air environment. Also, they need to be positioned where they are accessible. readily accessible. So maintenance and testing should be done easily. Again, making sure that they're not hiding somewhere that can be above the equipment pretty easily without doing too much as far as accessing them. Audio alarms have a sound pressure level of 15 decibels above the average ambient sound level and 5 decibels above the maximum sound level. So you may have to go a little louder for that maximum sound level depending on what kind of equipment you might have, let's say in a machinery room, or maybe outdoor noise, you're by an airport or a heavy industry area, a freeway. So you may have to look at that if it's not necessarily inside, it's also outside, that those sound levels may have to be adjusted to accommodate all that. Also, there should be some signage to identify those devices nearby. Something a little more visual to show the different levels of detection and alarm. There should be at least one detector provided in a particular room or area. Usually more than one is more than adequate, just depends on what kind of area you have and where we're talking about outside versus inside. And the level 1 alarms should activate a report to monitored location. We've talked about monitored locations a little bit in past webinars, and I'll kind of mention this again. Monitored location arguably is a 24/7 accessible person. So if someone is not answering their cell phone after hours, or maybe sleeping and not hearing their cell phone, that wouldn't qualify necessarily as a monitored location. So make sure you're addressing that when you're setting up these notifications, that it's going to someone that will see their phone, that'll wake up or answer their phone and know that something's going on and can call the correct people to address the problem. Level 2 alarms meet the requirements of level 1 and include an audible and visual alarm inside the room to warn that the access to the room is restricted, and emergency responders. So you may have to put 2 alarms on a particular room, let's say machinery room. You may want to put one in the machinery room in case someone is in there, and you may want to put one outside the machinery room so no one accesses that room when there could be ammonia in the room. So there's a little gray area here, but that's essentially what level 2 is talking about. Level 3 includes levels 1 and 2, plus control valves being automatically closed in the affected area, and possibly de-energized the operational equipment. So cutting off that electricity automatically, de-energizing those, making sure the control valves are shutting properly, and emergency exhaust systems being activated. Basically full controls on everything at level 3, and that I believe, if I remember from chapter, I believe it was chapter 14, was 100 or 150 ppm, and I did not put that in here, and I should have, but you can go back and look that, or if anyone needs that information, I can go ahead and look that up and supply it to you. Just real quick about the appendices, I didn't want to go through them because they're mostly informative. They support all the standards that are written, so I just listed a summary of what's in here, what's included. The information is helpful for reference, and includes calculations and examples on how to meet compliance. If you don't have a copy of the standard, I recommend it, but I just want to list appendices. There's some explanatory material that addresses general information that is provided in addition to the standard. There's also some general ammonia information specifically for the chemical. We get into Appendix C, that's calculations for relief valve capacity, nameplates for pressure vessels, and then getting into discharge capacity for compression relief devices, pipe hanger spacing, and specs on what should be used for supporting that piping, hydrostatic overpressure relief. Again, a lot of the pressure relief appendices do include calculations and equations to help work through those capacity problems. There's Appendix H talks about stress corrosion and cracking. Then we get into emergency pressure control systems, machine room signs, which gives you a couple examples of what kind of signs are required and how to effectively use your signage on the door of your machinery room or other doors in the facility. They also talks about alternative ventilation calculation methods. So looking at the ventilation systems and how to calculate that. Any requirements for pipe fittings, flanges, and bolting is in Appendix L. M is operational containment, and N is all the references and sources of references for the standard. So let's talk about what's next. IIAR Standard 9 is projected for a release in 2018. I believe right now they're just focusing on getting it done by the end of the year because it has to go through the ANSI process. It can be a lengthy process, and that's why they've been kind of pushing it back a little bit here and there. Right now they're scheduled for next year, and they're really pushing through on that. Once we have Standard 9, we have a defined scope of what RAGAGEP means in the ammonia refrigeration industry. We will have a set of standards that says, in order to meet RAGAGEP, this is what you have to do. But right now, we're operating a little bit in a gray area and using the design standards for new systems to apply to existing standards. So that'll be more helpful. It is important information to know. Until then, RAGAGEP still means striving for safer practice. So looking for improvements, providing feedback on IIAR 9 once I believe it was already released to the public. I'd have to ask Tony Lindell on that, and he might be laughing over there if he's listening. But I believe that they're in the process of finalizing all that, taking all the comments in. I'm sure they'd be happy with taking a little bit more comment. I don't know if they'd implement it, but some input is always helpful. Also, involving employees and personnel at your facility to address safety issues. They're going to notice things you may not if you're a manager and you're busy running around and doing all sorts of things, and your operator goes, hey, we've had, issues with this equipment, or, I saw that we could really use a sensor over here or whatnot. Make sure you're talking to your operators, your personnel, your employees, making sure that things are operating well, that you have some of the stuff in place, if not all, and any improvement areas to plan ahead. I mean, we all know that this costs money, and different facilities could be strapped for funds or whatnot. And so to plan ahead, having those projects projected out to be able to improve the system is important. Upcoming webinars and conferences. We actually have a webinar on November 6th for solids dispersion modeling that I did not put on here because I figured it probably wouldn't apply to most people here. But if you want more information on that, it will be available on our website, and we will be sending out an email as we normally do for that webinar. More pertinent to ammonia, we have a webinar on the general duty clause coming up in a couple weeks. We have another one on safety standards for gas-fired heaters in December. We have MOC and PSSR deficiencies coming up in January. Getting more into next year, we are going to have a workshop in Riverside. We're still working on the logistics on when and where, but that will be in partnership with Riverside County, and we'll be helping organize that for attendance. Also, we're going to be at the National IIAR Conference. I will be speaking there at one of the presentations, and also we will be exhibiting in a booth. A lot of you will see those emails go out as we get closer as to what booth and where to find us. If you have any questions, I'd like to open it up for questions now. And just a reminder that the audio and the PowerPoint will be available. We are recording, and we usually get it up in a couple days as far as getting up on the website. And I also will. Oh, okay, sorry, someone's talking to me over here. We will be getting this up on the website, and we will be sending out additional copies of the presentation to follow up. Oh, sorry, we got a mouse problem over here with trying to get the questions opened up. Actually, I'll just turn this off.
Thank you, Stephanie. So we do have a few questions. The first question is, do you know of any standards for maintenance and testing for hydrostatic pressure devices?
I do not know of any direct standards. I would have to look them up. I have a feeling they may have some stuff listed in the IIAR 6 still being developed, which was based on some of the bulletins. So I can go ahead and look at that. I'll take that question and look at that up later and see if I can find something. And I will also talk, I'm thinking of one person in our office that may know at least where to find someone who's certified to test, or maybe a resource for testing and certification.
All right, thanks. The next question is, what is the easiest way to implement RAGAGEP? There is a lot of information.
So the easiest way to implement RAGAGEP is probably to take on the easy things first. I mentioned the alarms and sensors. There may be some other easy things you can do with replacement of equipment. Perhaps I kind of mentioned it when we talked about level indicators. Perhaps your level indicators need to be replaced, and you can look at those, take a fresh look, and see if you can do anything different with those. Any kind of controls. I know a lot of people are upgrading their system to have the fancy control systems that can be controlled by phone and at home and from an iPad and everything else. So looking at those controls, and when you're upgrading, are you meeting all these new requirements with those upgrades? If you're changing out equipment, are you meeting these design requirements with your upgraded equipment? And also looking at your PHA. Is there anywhere that you can reduce the risk by removing either a safety hazard or removing the frequency or lowering the frequency of something occurring by changing your system around to make it safer? So PHA or the hazard review is also a good resource if you feel like everything else is covered.
Okay, the next question is, what might change with the release of RAGAGEP standard IIAR 9?
I mentioned a little bit about this before. The question was about what might change with IIAR 9 being released, and I mentioned that we'd have a more defined scope of what RAGAGEP is. The I guess the negative side for the facility is that the regulators will now have a black and white view of what is required or what they should be doing. The good side is the facilities will also have a black and white view of what's required and be able to address it directly. That is a benefit for facilities. We have been operating in a little bit of a gray area where there's a lot of suggestions and a lot of shoulds, but there's no requirements per se. There's also a lot of digging around to do. All these requirements will be in one place now for the most part. I wouldn't say maybe all, but you're talking about at least 90% of the requirements for RAGAGEP for our facilities would be in one place. So you wouldn't have to dig around into the compressed gas standards or into pressure vessel standards or looking at ASME versus IAR versus the old bulletins or whatever else. It would all be in one place for you. So there are some good things that will come out of this. Also, just generally what I see from an engineering perspective is a lot of people are already implementing this stuff. So it's not going to be as negative, I think, as some people think it will be, but it is going to give the regulator some ammo because now there will be some defined standards that are set in place.
All right, thank you. There is one last question. Does RAGAGEP have anything to do with the general duty clause?
So I mentioned that we're going to have a presentation on the general duty clause in a couple weeks, and they do overlap. They're very much related. However, there's a lot of differences as well. While they both aim to um, provide safer operations and safety for the employees and local community, um, RAGAGEP really applies to Program 2, Program 3 facilities that are already under program regulations but may need a little bit more. General duty clause really covers the unregulated facilities. So for those that are under threshold limits, and also those that are program 1, where they might not have to do some of this extra work for program 2, program 3, but who may need to. It's very interesting. Again, it's a whole nother topic. If you are the unregulated or program 1 facilities, I highly recommend that you watch it or catch the recording later. For program 2, program 3, there is some useful information in there, and we will be gauging it to try to bring you guys in as far as interest level. But there's, if you have a program 3 facility, you're probably already meeting the general duty clause. Program 2, there's still a little bit of a gap, and really getting down into the lower parts of the threshold limits and unregulated facilities is where we're targeting this.
All right, thank you, Stephanie. That's all the questions.
All right. Again, the recording will be available soon, and thank you for listening.